So let's look at this problem. I left class last time with this problem where we had a block on an inclined plane and I left some information off. So let's work through this and realize what's going on. So we have this block that starts here, the bottom end of the plane, and it moves with motion up the plane. And I state that it's moving. I think I stated in class that it was moving with constant velocity. But you guys were clear that the acceleration in the x direction was zero. We also set the the positive side of the x axis is going downward. And it doesn't matter as long as you're consistent. We have an angle for this incline here of 30 degrees. We're going to call that phi because later on when we look at our work equation, you'll see that theta is often used. So we just want to be careful. The mass of the block is 10 kilograms. The coefficient of kinetic friction is 0.4, and the displacement up the ramp is 5 meters. Now keep in mind this displacement is always positive, a positive number. Even though it's going in the negative direction, we constitute that as positive. And so if we look at our free body diagram over here, just basically concentrating that mass of the block into a single dot, leaving the ramp there just so that we have some reference, we can see where all of the forces are. Now, the mistake that I made was I forgot to give you the pushing force. In order for this object to maintain a constant speed, and in other words, zero acceleration, the two forces should be forces in the x direction would need a force to cancel the other out. Okay. And so I called that a pushing force. And so how did I come up with these forces going down the ramp again? All right, so we know that because motion is going up the ramp, and we have friction here, that friction is kinetic friction. We also kind of know that weight is going towards the center of the earth or towards the bottom edge of our paper, perpendicular to that. But that needs to be resolved because it's not in line with our XY axis. So we always typically want to resolve forces that are not in line with our axis. You can see it's in this direction and our axis needs to be, we set it up so it's perpendicular to the surface of the board in the Y direction and in line with the plane. So we resolve that vector. So that vector kind of goes away. It's summed by these two vectors, w sub x and w sub y. Decompose the vector that way. If you're having a hard time with that, just make sure you look at this triangle here. Here's my w sub x. Here's my w sub y. And here's w. And this angle right here is that angle phi, which was also this angle right here. Okay. So go through the trigonometry. This is the right triangle, by the way. You'll see how I came up with those values. That's going to be very, very important for you. So make sure you do your due diligence and you do the work on that. So F of P is the force that we left off. So I do a lot of calculations over here. Remember what our goal was, by the way. Our goal was to find the work done by kinetic friction. and I know it's a little bit cumbersome and you probably won't see this too much in the book. I like to just write it all out with an F of K here so that it doesn't get conflicted or doesn't overlap what W is in terms of weight. Weight is often used for with the abbreviation W. Okay, so then I go through a bunch of summation equations. So how did I come up with these? Well, we have F of K, which is down the ramp, which is positive. We have our weight component in the X direction. When we resolve it, that's this mg sine phi. And we also have the pushing force. That's the force that's going to basically counteract the sum of those two forces to allow this block to move with a constant speed. Okay. And we go through some finagling here. We try to solve for F of P, what that pushing force is. And then F of P turned out to be 82, roughly about 83 newtons. Then we summed in the Y direction. In the Y direction, it's pretty straightforward here. We have our normal force perpendicular to the ramp and our weight component in the Y direction. So those two cancel each other out. And again, the reason is that this block, you think about the block moving in the in the negative X direction as such, my head, as such, it is not accelerating in this direction. Okay. So when we look at the forces in the Y direction, we can set that equal to 0. We can solve that for the normal force, and our normal force comes to be about 85 newtons. So now we look at F of K. I did F of K over again for you. You calculated it over here in this equation, but by definition, F of K, you want to keep this in mind, F of K is equal to mu sub K times the normal force. Mu sub K was given, the normal force we found in this summation. So again, we'll see that it's 33.95 newtons. So the work that F of K does, here's our definition. I plugged in, but in general, it's going to be the force in question multiplied by the displacement, how far it moves. And that displacement always is a positive number, so you take the absolute value of it, multiplied by the cosine of theta, where theta is the angle between the force in question and the displacement. So one more time, let's look at where everything lines up on the board here. Get this thing to move other way. Okay. So you can see that kinetic friction goes down the ramp. Our displacement vector, it's not drawn here, but it's in the same direction as F of P. So we're moving up the ramp. Those two oppose each other. We compare the forces by looking at them tail to tail. So again, our displacement vector, maybe we call it D, goes in that direction. Kinetic friction, F of K here, we form 180 degrees. And that's what we, in this case, we just call theta. So very tail end over here, we figure out the work done by kinetic friction. It is the force itself, magnitude, about 34 newtons, times the displacement, times the cosine of 180 degrees, which is -1. So frictional forces tend to do negative work on an object. And if you forget that the units are joules, you can always write for me the units that are just kind of outright. So this is in newtons, and this 5 meters is in obviously meters. So this would also be equal to negative 170 Newton meters. Okay, so either one of those is correct. All right.